Hello and welcome, class, to a brand new semester if you are watching this in the spring of 2021. Otherwise, feel free to enjoy the lecture. You're probably just following up from Chapter 10, Part 1, and you haven't noticed any type of, time lapse or anything. When we last spoke, or rather, in Chapter 10, Part 1, we defined some basic terms in thermodynamics, like surroundings, system, first law of thermodynamics. We talked about that. And where we are picking up is with the concept of enthalpy. What enthalpy pertains to is the energy associated with a particular chemical reaction. So, as this is a chemistry course, we're going to be talking about the energetics of chemistry, right? Energy in, energy out. How does energy play a part in chemical reactions? All right, so let's define thermochemistry. When you break down the word, it is defined exactly how you would expect it. Thermo pertaining to heat, chemistry pertaining to chemical reactions. Thermochemistry is the study of heat transfer associated with chemical reactions. So again, this is going to be either energy in, as a certain object or reactant or chemical is going to require energy to break bonds over the course of a chemical reaction, or if the chemical reaction itself is too full of energy, there is going to be energy coming out from the reactants over the course of the reaction from reactants to products. Now, enthalpy is the measure or the quantity of heat per mole that is going to be exchanged during the chemical process. So thermochemistry, we're looking at heat in chemical reactions. Enthalpy is the way that we quantify that heat. The variable for enthalpy is going to always be delta H. H for enthalpy, the delta because we are looking at a change of heat, right? So what's the difference between reactants and products? How much heat gets released on a per mole basis? Now below we have an equation. Q is equal to N delta H of reaction. Q, as we saw last semester or in Chapter 10, Part 1, is our variable for heat. Just a magnitude of heat, a quantity of heat. It doesn't necessarily have to be associated with a chemical reaction. It's just the heat itself. The amount of heat that is going to either be released or absorbed net as a part of a chemical reaction is going to be equal to the number of moles of the reactant that are going to be consumed during the reaction times the enthalpy of reaction. Right, so enthalpy is the change of heat on a per mole basis, so you multiply it by the number of moles you're actually reacting, and you can find the amount of heat that you're expecting to be exchanged over the course of the chemical reaction that you are specifically working with. So the setup of this equation we're going to be using a lot, not just in this chapter. The spring semester is all about taking what we have learned in the first semester and just pushing it one step further. We're going to be looking at it one notch deeper. So we're going to be looking at a variety of enthalpies. We're going to be calculating a variety of heats throughout this semester, but the basic form of this equation will always remain the same. There are two different directions that the flow of energy can take. Either energy can go out from the reaction, or it can be sucked into the reaction, all depending on what the reactants need to turn into products. An exothermic reaction is a reaction in which the energy that we are observing is being released to the surroundings. What this means is that the sign of the enthalpy, the sign of the delta H, is going to be negative. The negative sign when it comes to energetics is pure direction. If your system, this little ball here representing the system, is releasing heat to the surroundings, heat going outwards, what this means is that the system is losing energy. The surroundings which is everything that's not the system. As a reminder, the surroundings may be gaining the energy, but the system is what is losing it. And so if the system is losing energy, this must mean that the sign, the direction, is negative. So everything in chemistry is relative to the system. Everything in chemistry is relative to the reaction. So this is why enthalpies, if they pertain to exothermic reactions in chemistry, have negative values. Now, a way to keep track of exothermic versus endothermic is how it feels to the surroundings, because we as people count as the surroundings. So how would we observe, or how would we interact with this chemical reaction? Exothermic reactions feel hot. The most famous exothermic reaction has to be combustion. So let's say there's a little campfire sitting here, you got a fire burning off from the coals, burning off from the logs, consuming that fuel, and a person is standing nearby to keep warm. It's because the reaction is giving off heat. The reaction is losing heat, and you here, as the surroundings, are going to be picking that up. So you're going to feel nice and toasty. Now, how we represent this loss of energy can also be seen in the form of a potential energy diagram below, where the energy is presented on the y-axis and time is presented on the x-axis. So notice that we don't have any specific tick marks. We're not measuring this super quantitatively. We're just getting an idea for the general form here. The reactants are going to start with a particular energy level. Doesn't matter exactly where, so we're just going to put them right in the middle. And over the course of a chemical reaction, we're going to have to put energy in. Doesn't matter what reaction we're working with. Energy in corresponds to bonds breaking. All reactions must have a little bit of energy that we put in, right? Even with combustion, we have to enter or add some type of spark. There's no such thing as pure spontaneous combustion, right? There needs to be some level of energy put in order to break the first bonds that need to be broken. The big difference is what happens after this. How we consider an exothermic reaction, why the energy ends up leaving the reactants. Yes, we have to put a little bit in, but after these bonds are broken, we can see that the products are now much lower in energy than the reactants were at the beginning. This difference in energy, if we were to carry this dotted line all the way over, we can see gives us a net internal energy of our products that is lower than that of the reactants, which is ultimately what gives us, mathematically speaking, a delta H, an enthalpy that is less than 0, meaning it is negative. So if our delta H of reaction here is some type of negative value, let's say it's negative 10 kilojoules per mole, just picking out a random number, and we are reacting 1 mole's worth of substance, this must mean that there was a total of negative 10 kilojoules of energy involved with this chemical reaction. And the negative sign, again out in front, signifies that 10 kilojoules were lost or released by the system. So if you see the language like lost or released in a textbook or a worksheet or a homework problem, what this means is that there is a negative sign out in front of your Q. There's a negative sign out in front of your delta H. The second form that our energetic reactions can take is that of an endothermic reaction. So in contrast, just to go backwards again, exo in the exothermic, in terms of Latin prefixes, means to go out from. Exo literally translates to going out. The energy is being released. Endo, the opposite perspective, is more internal. It means that we are going within. And of course, this appropriately named type of reaction pertains to when energy is going to be taken in from the surroundings. What this means in terms of the actual quantification of our enthalpy is that delta H is going to be positive. This is because our system, whatever the reactants are, is going to be taking energy into itself. It is going to be literally gaining heat. So we're going to add a little plus sign there, smiley face. The system is going to be gaining energy. Now with my smiley face here and the frowny face on the previous slide for exothermic, I don't want there to be some misunderstanding that exothermic is bad, endothermic is good. I'm just using the smiley face and the frowny face in terms of the positive versus negative association. That tangent aside, let's continue actually observing our endothermic reactions. So the sign of delta H is positive. We are going to be gaining heat. This means that the surroundings are going to feel cold, right? Again, people are a part of the surroundings. Unless you yourself are physically or chemically involved with the chemical reaction, you are going to count as a part of the surroundings. So if the system is picking up heat, that must mean that you as a part of the surroundings are going to be losing heat. Heat is going to be moving away from you and into the system. This means that endothermic chemical reactions tend to feel cold to anyone who is observing them. Now we can plot the potential energy difference, right? Potential energy on the y-axis versus time on the x-axis, just like how we did before. The reactants will start with some particular energy level. Doesn't matter exactly what in this case, we're just looking at the general shape of this curve. One thing that the endothermic reaction has in common with the exothermic reaction, we can see is a certain amount of energy does need to be added in order to break bonds. Right, that happened last time, that will always happen. If you're observing a chemical reaction, that must mean that bonds are breaking, new bonds are going to be forming. The difference between endothermic and exothermic is what happens afterward. After the bonds break, we're going to see a lowering in energy as new bonds are formed. However, the products of an endothermic reaction are higher in energy level compared to the reactants. So if we take the product value for an enthalpy and subtract out the reactants, we would end up with a positive delta H. Now a positive delta H when working with our equation from before will obviously then result in a positive Q. If our delta H here is a positive 10 kilojoules per mole, and again, we're multiplying this delta H by 1 mole. Let's say we're reacting 1 mole of, some chemical species. This must mean that 10 kilojoules are involved with this chemical reaction. And that 10 kilojoules is going to be positive. If you are reading along again in like the textbook, you're reading certain homework problems, a quiz problem, a test problem, any type of problem, reading an online resource, whatever the situation is, if you see language like gains or absorbs 10 kilojoules, the gains/absorbs, specifically it pertains to this positive sign. Again, we're always from the perspective of the system in chemistry. And so if we see that, the language surrounding a problem or describing an observation states that certain amounts of energy are gained, the enthalpy or the heat, our Q, have to be positive. So far, the enthalpies that we have been talking about in the diagrams we've been observing all pertain to chemical changes. Well, what difference does it make if we are looking at a chemical reaction versus a physical reaction? Something in which chemical bonds are not, covalent bonds aren't breaking, ionic bonds aren't breaking. What happens if we're just breaking the intermolecular forces and we're changing phase, let's say, from gas to liquid, hypothetically, right? We're taking a gas and we're condensing it down into a liquid. Well, anytime the temperature of a species is changing, this must mean that the internal energy of that species is changing, since temperature and energy are intrinsically linked. Physical changes are consistently also exothermic and endothermic from the perspective of energy. An exothermic physical change would be anything that has to do with condensation. So if we're going from gas to liquid, or if we're condensing even further from liquid to solid. Now this may seem a little counterintuitive because we're going from something that's warm, like a gas, to something that's cool, like a solid, like how can that be an exothermic process? Well, we have to remember what it means to be exothermic. Exothermic means that energy is leaving your system. Well, gases are pretty energetic. They are high energy, right? This is what allows for these particles to be separate and distinct in the first place. These particles are separated from each other because they have very high energy and relatively high temperatures, right, compared to their liquid and solid counterparts. If we want to take a gas and condense it into a liquid, we're going to have to take this energy, this high internal energy, and disperse it to the surroundings. Since the energy is going to be dispersed outwards to the surroundings in order to cause a gas to condense into a liquid state, this is the literal definition of an exothermic reaction. The energy must be lost in order to transform your gas into a liquid. Even more energy is going to have to be lost if we want to transform that liquid into a solid, right? If we want to freeze something, we really need to make sure that the energy internally of that species is low and that its temperature also is going to be relatively low. So an exothermic physical process is one of condensation. Even though if we're thinking in terms of temperature, it may seem counterintuitive, if you are keeping your perspective on that of the system and its energetics, you should never have a problem keeping track of whether or not condensation or vaporization is exothermic versus endothermic. Just got to keep track of the system, ignore the sensation that you would feel as the surroundings. We're always looking at this from the perspective of the system. I'm going to clean this slide off for the next discussion, the endothermic discussion. Boop. Endothermic, of course, is going to be the opposite. We're going to have to take a substance at low energy, that of our solid, which has very low energy, and we're going to have to give it some energy if we want it to melt. Right? If you want to take an ice cube and turn it into liquid water, you're going to have to put energy in. You're going to have to raise its temperature. You're going to have to hold it in your hand. You're going to have to put it on the stovetop or in the microwave or leave it in the sun. If you want to melt an ice cube, you have to give it energy. And if energy is being absorbed, this makes the transformation of solid to liquid an endothermic process. Now, if we want to make the next jump from liquid to gas, we're going to have to absorb even more energy. Energy goes into the liquid to take each of these individual particles and separate them. Right, we're going to take the liquid and we are going to separate each of the particles out into these distinct locations separated by distinguishable distances. And in order to do so, we're going to have to really jack up the internal energy of our system. So whether we are thinking chemical change or physical change, if there is a change in energy, we're going to have some type of associated enthalpy with that change. All right, so let's return to chemical reactions. Let's also look a little bit more quantitatively, not in a hypothetical sense, but let's observe a real world kind of problem. Let's calculate the total heat change when 11.8 times 10 to the 3 grams of propane, which is also chemically C3H8, is burned. 11.8 times 10 to the 3, first of all, is not proper scientific notation. I'm going to slap myself on the wrist for that. It's just an easier number to look at. It's an easier number to work with. This is 11.8 kilograms. This mass is the mass of your average, 3 liter container, or 3 gallon container of propane. In addition, we're going to observe whether or not this reaction is exothermic or endothermic. And below we can see the chemical reaction for the combustion of propane. No specific phases are included. We don't need to worry about that right here. We're just looking at the reaction as well as the enthalpy that is provided. So we can see that the enthalpy for this given reaction is equal to negative 2,202 kilojoules per every single mole of propane that gets burned. So our first step in solving this problem has to be to figure out how many moles of propane we're actually working with. And once we know how many moles we're working with, we can use our enthalpy to calculate the total amount of heat exchanged. All right, so I'm going to let you guys pause the video, or rather I would suggest that you pause the video, see if you can't work through this problem yourself, and then we can come back together and compare our answers. All right, so welcome back. Let's start from the end and work our way to the beginning. Is this reaction exothermic or endothermic? Well, in order to answer that question, all we need to do is look at the sign of our enthalpy. Right, again, exothermic reactions are always negative in terms of enthalpy because energy is being released from the system. Endothermic reactions are always positive because energy is being gained by the system. Since our delta H of reaction here is negative, must mean that we are working with an exothermic reaction. This analysis, this conclusion, also agrees with what we know of combustion. Combustion is a very violent and hot chemical reaction to those of the surroundings, right? That's why we always enjoy a good bonfire, or why propane, for instance, and its combustion are used for heating things on the grill. So whether you relied on previous information, past experience, or you went just straight for looking at this negative sign on your enthalpy of reaction, you would have been right, and it's good that these experiences align and come to the same conclusion. All right, so now that we have addressed whether or not it's exothermic or endothermic, let's actually calculate the net amount of heat, the magnitude of heat that is exchanged when we are actually burning this propane. So we're going to start with 11.8 times 10 to the 3 grams of propane. And we want to convert this into numbers of moles of propane. The reason why we want to do this is, again, we are looking for a heat change, and heat is always Q. The equation that we have learned so far today is Q is equal to N delta H, N being number of moles, delta H being our enthalpy. If you didn't remember this equation, you would not be totally stuck or in the dark, because as was a popular phrase that I would use in the fall semester, I'm going to keep using it. All you have to do is follow the units. If you're trying to find a heat, which is oftentimes measured in units of joules or kilojoules, and you can see that you're given a value that is in kilojoules per mole, the way that you get rid of the mole in this denominator of the unit here is by multiplying by a number that is in the unit of the mole. Therefore, moles will cancel out. So whether you have the equation or you're just following the units, the actual process is going to be the same. So let's convert the grams into grams into moles, not kilograms, by dividing by the molar mass, which is 44.09 grams all per 1 mole. And we can explicitly calculate the number of moles here, but since grams have now canceled and whatever number I would calculate is in the unit of moles, let's just say that this is our N. I'm going to save myself on some calculator time, and I'm just going to multiply this by the enthalpy straight up, which is negative 2202 kilojoules per mole. Right, this is our delta H. So we're taking N times delta H. This is going to give us some value of Q. So 11.8 times 10 to the 3 divided by 44 times negative 2202 gives us a total value of negative 5.89 times 10 to the 5 kilojoules. And this is going to be our magnitude of heat. So in reporting this answer, I could say that 5.89 times 10 to the 5 kilojoules was released, or I could say Q is equal to negative 5.89 times 10 to the 5. Both of those two phrases would mean the same thing. All right, so with the first example problem out of the way, let's just look at another, right? This semester, again, is going to be much more quantitative. We're going to be performing more analyses than what we did in the first semester. So we're just going to get in the habit now of just practice with these types of quantitative problems. The reason why I like this problem is the approach is a little bit different than the first. I mean, the fundamental approach is the exact same, but there's a little bit of a twist. So delta H of reaction, as it turns out, is dependent on the stoichiometry of the reaction. Now, we didn't have to really look at the chemical reaction in our previous problem, and I'll explain why as we start approaching this problem. We are charged with calculating the heat change when 1.5 moles of methanol, CH3OH, is burned, according to the chemical reaction below. And here we see a fundamental difference between our reaction here and the combustion of propane before. That difference is that there is a coefficient in front of the methanol. In our previous equation, just to go backwards, there was a coefficient of 1 in front of our propane. And as we all know, multiplying by 1, dividing by 1, it doesn't change the answer at all. So we didn't really have to look at the chemical reaction. We didn't have to consider what the stoichiometry of our reaction was. In this problem, we do. Because remember, our enthalpy pertains to kilojoules released or absorbed on a per mole basis. And here we can see that the number of moles in front of this CH3OH not being equal to 1 is going to have a difference on how we calculate the total amount of heat change, our Q. The big question is, how do we incorporate this 2? Do we have to multiply our answer by 2? Do we have to divide the answer by 2? Like, what do we do with this 2? Because the 2 corresponds to the standard enthalpy that is reported over here, this negative, circle it like that, this negative 793.2 kilojoules per mole. If we want to get rid of this 2, we're going to have to, as we've seen before, since all of these coefficients are just ratios of reactants and products, if we want to get rid of a coefficient, you can't just erase it, you can't subtract it out, we have to divide. This is how our ratios work. We can scale up by multiplying, we can scale down by dividing. So what we're going to do, and it may look strange, but this is what we're going to do, we're going to divide each of the coefficients out in front of our species by 2. In doing so, we're going to remove the 2 from the methanol. This is going to cancel out. 2 divided by 2 is equal to 1. Well, since our enthalpy of reaction, again, corresponds to the reaction as it was written, with coefficients of 2's in front of things, we are also going to have to divide this enthalpy by 2. If it pertains to the reaction, we are scaling it down by a factor of 2. Regardless of the type of reaction you are working with, if the species of interest, which is normally referred to in the problem, like how this methanol was referred to in the problem, we're going to have to observe in the chemical reaction where it is and what the coefficient in front of it is. If you have a coefficient that is not equal to 1, so if you have a 2 or a 3 or a 4 or whatever the number is, you're going to have to scale your entire reaction either up or down such that the coefficient in front of that species of interest becomes 1. When you do that, you're also going to have to scale your quantitative enthalpy, this delta H, up or down by the same value. We're just going to, in this case, explicitly divide by 2 across the whole board. And this is going to give you the true enthalpy of reaction per every 1 mole of methanol that gets burned. Okay, so we can calculate explicitly what this new enthalpy is, negative 793.2 kilojoules per mole divided by 2. I'm going to keep it just as this fraction for much the same way as I didn't explicitly calculate moles in the previous problem. Sometimes it's easier just to save all of your math for one big calculation. And because this equation that we are working with, Q is equal to N delta H, is a pretty straightforward equation to use, I'm just going to insert this whole enthalpy as a fraction into this equation. So the number of moles, we are told we have 1.5 moles of methanol, 1.5 moles of methanol. And now that the entire reaction has been scaled down such that the coefficient in front of methanol is 1, the enthalpy that we have, also divided by our 2, the 793.2 kilojoules per mole divided by 2, corresponds to the enthalpy such that we are only burning 1 mole of methanol, according to the chemical reaction. Now we know by the wording of the problem, we are actually burning 1.5 moles of methanol. So another way to think about how we're approaching this problem is we scaled the coefficients in front of the methanol down by 2, and now by multiplying by 1.5, it's like we're scaling it back up. And we're doing the exact same thing to the enthalpy. We scaled it down by 2 because that was the value, the coefficient in our chemical reaction, and now we are scaling it back up by 1.5. And the reason we're doing this is because ultimately we're asked to find what's the heat change when we're burning 1.5 moles of methanol. So we're always going to scale down by the coefficients in our reaction and scale up by the amount or the magnitude of stuff that we're working with that is given to us in the wording of the problem. Scale down by the coefficients in the reaction, scale up by the magnitude that we're given in the wording of the problem. All right, so at the end of the day, we're going to be taking our 1.5 times negative 793.2, dividing it by 2. Our moles are going to cancel out, giving us a final value, negative 594.9 kilojoules. Well, now that we have introduced conceptually what enthalpy is, and we've seen a couple of qualitative problems as well, calculating enthalpies and heats, let's turn our attention to a more standardized approach. Right, where did those enthalpies that I gave you for those 2 previous reactions even come from? Well, we can calculate standardized enthalpies of reaction from enthalpies of formation. So what is an enthalpy of formation? First and foremost, it is a specific type of delta H with a subscript of an F pertaining to formation. It also has this fancy superscript of, it looks like a 0. What it actually is, or how it's pronounced, is not. So we would say this is delta HF not. And what the not represents is the word standard. What does that mean? So a standard enthalpy of formation is a measured enthalpy where specifically the pressure and the temperature were held constant. The pressure was held at 1 atmosphere, and the temperature was held at room temp, or 298 Kelvin. In addition, the standard enthalpy of formation is always relative to 1 mole of the product. Formation pertains to the formation of a product. So we can also keep in mind what formation means, what why we call it an enthalpy of formation. It's because over the course of a chemical reaction, we form a product. All right, so let's say experimentally, we perform the following reaction below. We have 2 sulfurs, we combine them with 2 oxygens and 2 elements in their natural state, in other words, and we get this cool product of sulfur trioxide, SO3. Well, over the course of the chemical reaction, assuming we took a measurement of what the initial reactant's energy levels were, where again, energy is going to be on our y-axis, time is going to be on the x-axis. The reaction took place over a certain amount of time, the chemical bonds of the reactants had to be broken, and our products, should be a flat line, our products are going to also have a particular energy level, and the difference between these 2 is going to give us a measurement of our delta H, right? Just as a reminder from our diagram that we saw previously in this lecture. This delta H was calculated at standard pressure and temperature to be equal to negative 792 kilojoules per mole. So experimentally, we can find these delta H values. We're actually going to be seeing a couple of labs where you guys are going to be finding enthalpies yourselves. We're going to get some good practice seeing how these energetic experiments are performed. However, recording every enthalpy for every individual chemical reaction known in existence would just be an exhaustive list. This is where the standard enthalpy of formation really comes into play. It's much easier to write down or record in a table to be shared or printed what the internal energy of a particular molecule is instead of a chemical reaction. In doing so, that particular reactant, or product in this case, whenever it's involved in a reaction, all we would need to do is turn our attention to its standardized enthalpy of formation to get a better idea for how much energy that one species actually contains. If it's a reactant, its energy will be this high or low on the reactant side. If it's a product, it would be this high or low on the product side, relative to everything else that's present. So, how we find enthalpies of formation from these experimentally determined enthalpies of reaction is by using stoichiometry, just as how we did in our previous example problem to scale a reaction up or down, such that the coefficient in front of our product is 1. So we can see in our chemical reaction here, there are 2 sulfurs for every 3 oxygens, and they produce 2 sulfur trioxides. We are going to divide everything by 2 to make sure that this coefficient in front of the sulfur trioxide turns into a 1. And if we scale a reaction up or down, we must also scale the enthalpy up or down. Since we're scaling this reaction down by a factor of 2, our delta H, actually I'll do it down here, delta H of formation for SO3 is going to be equal to a negative 396 kilojoules per mole. So let's see what I mean by that. Let's see how we then use these enthalpies of formation. This is how they're found, but it's more common for us to use them instead of finding them, because as it turns out, our textbook actually has a table in the appendix of nothing but enthalpies of formation for, hundreds of different compounds. So how do we use those? How do we take advantage of the predictive power of knowing what the internal energy of a molecule is? Well, we can experimentally find enthalpies of reaction, but it's kind of difficult to get into the lab to test every single enthalpy when you need to know what its numeric value is. Instead, we can calculate a standard enthalpy of reaction from using nothing but a combination of enthalpies of formations for the products and the reactants. The standard enthalpy of reaction is the enthalpy of a particular reaction that takes place under standard conditions. Again, we have this little naught symbol here, meaning that we are at 1 atmosphere and 298 Kelvin, just to keep in mind, again, what standard conditions are. To find or calculate the standard enthalpy of a reaction for whatever reaction we're observing, all we need to do is take the sum of all of the enthalpies of formation for our products, multiply each of them by our stoichiometric coefficients, and we are going to subtract out the sum of all of the enthalpies of formation for each of the reactants, also multiplied by their stoichiometric coefficients. So our standard enthalpies of formation tell us what the internal energy, relatively speaking, for each of these molecules is. Once we have the context of a chemical reaction, we know how to use them and predict what the enthalpy of that particular reaction will be. And I said that our textbook has, and if you're in my class specifically, we're using Burge and Overby's 4th edition, so if you're in a different textbook, the appendix label might be different. For us, all of the enthalpies of formation are in Appendix 2 of the text, and again, there's hundreds of compounds there. So we saw how to find an enthalpy of formation from a given enthalpy of reaction. Let's see how to find a more complicated enthalpy of reaction using nothing but enthalpies of formation. In other words, we saw how to solve this problem in one direction. Now we're seeing how to solve the problem going the other direction. All right, let's find the enthalpy of reaction for the combustion of methane. It can be kind of difficult to measure the internal energy of gaseous carbon dioxide and water since, at the end of a combustion reaction, everything's on fire, it's dangerous. And we have means to do this, don't get me wrong, but let's see how to, even without stepping foot in a lab, predict what the enthalpy of reaction in standard conditions for the combustion of methane would be. And we're going to do so using nothing but recorded enthalpies of formation. So in the table below, these values I pulled from Appendix 2 in our text. So methane in gaseous form has an internal energy of negative 74.81, which is found here in our chemical reaction. Let's do that. Carbon dioxide in gaseous form has an internal energy of negative 393.5 kilojoules per mole, and that's right there. Water in its liquid state has an internal energy or enthalpy of negative 285.8 kilojoules per mole, and that's over there. And last but not least, oxygen has an internal enthalpy of 0? Well, let's talk about this. Obviously, oxygen is, especially in gaseous form, doesn't have 0 energy, right? It has to have some energy, otherwise it wouldn't be a gas. What's really important about this 0 and what it signifies is how we've standardized our measurement of enthalpies. You see, energy slash enthalpy is always relative. Is something higher energy or lower energy? And if so, what are we comparing it to? Well, as it turns out, the way that we have standardized in the scientific community our measurement of energy slash enthalpy is by saying any element in its natural form has a 0 enthalpy. So oxygen in its gaseous state, charcoal, like carbon, in its solid state, N2 gas, nitrogen's natural state, silver in its solid pure form, each of these pure elements has a 0 enthalpy. And so each of the molecules that are present inside of the Appendix 2 table, or from what we can see here in this extracted version of the table with our methane, our carbon dioxide, and our water, each of these things have non-zero enthalpies because they are not pure elements. For example, the enthalpy of formation for water, which contains 2 hydrogens and 1 oxygen, is negative 285.8 kilojoules per mole more stable than the combination of hydrogen and oxygen in their naturally occurring forms. So that is why each of the molecules have non-zero values and all of the elements have 0 values. The 0 values pertain to elements in their natural form, and this gives us an idea for either how much more stable or how much more unstable molecules are compared to this natural state. All right, so now that we have disclaimed our oxygen and why it has a 0 kilojoules per mole, we're going to use it as a 0, right? Again, everything here is relative. But we can use all of these values, each of these enthalpies of formation, to predict when we have this particular combination of reactants and products, what should the resulting enthalpy of reaction be? I don't really have space to work on this slide, so I'm just going to come to this blank slide. I'm going to keep going back and forth to grab information that we need, but the blank slide is going to be useful for actually writing out my work and make sure I have the space to make it clear. Our enthalpy of reaction is going to be equal to the sum of the coefficients in our chemical reaction N times the enthalpies of formation for our products, and we're going to add to that the sum of the coefficients in front times the enthalpy of formation for the reactants. It's not plus, sorry, it's minus. We're subtracting here. Products minus reactants. We always take the final minus the initial, right? The end minus the beginning. All right, so let's just go observe our products. On our previous slide, we're going to start pulling the numbers and rewriting them onto this work slide here. Our first of the products is carbon dioxide. We can see that there is a coefficient of 1 in front of the carbon dioxide, so we're going to take 1 times 393.5 kilojoules per mole. 1 times negative 393.5 kilojoules per mole. And we're going to add to that, because we're taking a sum, the other product. Now we can see that there are 2 water molecules, which means we're going to have to take 2 times negative 285.8 kilojoules per mole. 2 times negative 285.8 kilojoules per mole. And we can see that based off of our chemical reaction, these are both of the products. There are no more products. So here in our work is where we're going to close off this parentheses. We have now finished this section of the equation, and we're going to subtract out the sum of all of our reactant conditions. The first of our reactants is the methane, we can see here. So we're going to take 1, since this is the coefficient in front of our methane, multiply it by the negative 74.81 kilojoules per mole. 1 times negative 74.81 kilojoules per mole. And we're going to add to this 2, because that's the coefficient in front of our other reactant, times 0. Right? Again, our oxygen is in its natural state, so it doesn't have an internal energy relative to the other reactants and products. It technically does, but since everything is relative, we have set the scale to our naturally occurring elements, and so oxygen, we just consider its internal energy here, its enthalpy, to be 0. All right, but we have filled in everything that we need to fill in, both of our products being taken into account, both of our reactants being taken into account. So now we can just crunch the numbers. And if we crunch the numbers on our calculators, what we find is that the enthalpy of reaction for the combustion of methane would be negative 890.3 kilojoules per mole. And we didn't even have to step foot in a lab to figure that out. All right. Well, congratulations for making it to the end of chapter 10.2 in particular, because this is the first real lecture of my spring semester in 2021. If you would like some additional practice, here we have a couple of example problems. The first section of review problems corresponding to the enthalpy section, our first conversations of Q is equal to N delta H. Here we have 3 example problems that can be found on page 429. The second set of problems correspond to our standard enthalpies of formation. So these are going to be our delta H of reaction is equal to the sum of N delta HF product minus sum of N delta HF reactant. So if you'd like some more practice with our second set of enthalpy problems, you can turn your text to page 446. We have 3 additional problems that I would recommend there. Now, if you are new to my section in the spring semester, I never collect these problems, right? If you're watching this online just for like review, or if you have to like miss the first couple of days because again, COVID-19 is a thing during this academic year, like totally fine. These are for you. Like I'm never going to collect these from you, but I do recommend them if you would like some extra practice, in particular because we are going to be working with these 2 equations a lot this semester. Not consistently, but off and on enough that it's going to be important to remember. All right, well, hopefully this first lecture wasn't too rambly after Christmas break. Again, if you're watching this not in the spring of 2021, who knows what the situation is and why you're watching this, but hi and welcome anyway, and I hope you found it enlightening. If you have any questions, do not hesitate to email me if you are in my class. Otherwise, feel free to leave a comment below. And until next time, class is dismissed.